Hi everyone, my name is Anjali and I am a pre-final year student currently pursuing my BTech degree in Computer Science and Engineering at IIT Guwahati. Today, I am going to talk about the concept of segmentation and paging in Solaris. We will learn the memory architecture and how memory management takes place in Solaris operating system. Before we begin, let me just give you a brief about segmentation and paging. Let's start with segmentation first. Segmentation is a memory management technique in which the memory is divided into variable size parts. Each part is known as a segment, which can be allocated to a process. The details about each segment are stored in a table called as segment table. It contains mainly two information about segment. First is base and second is limit. Base represents the base address of the segment, whereas limit represents the length of the segment. Now, the CPU generates a logical address which contains two parts, namely segment number and an offset. The segment number is mapped to the segment table. The limit of the respective segment is compared with the offset. If the offset is less than the limit, then the address is valid, otherwise, it throws an error as the address is invalid. In case of a valid address, the base address of the segment is added to the offset to get the physical address of the actual word in the main memory. Now, moving on to paging. Paging is a storage mechanism used to retrieve processes from the secondary storage into the main memory in the form of pages. The main idea behind the paging is to divide each process in the form of equal-sized pages. The memory is also divided in the form of frames. Considering the fact that the pages are mapped to the frames in paging, page size needs to be as same as the frame size. When a page is to be accessed by the CPU by using the logical address, the operating system needs to obtain physical address to access that page physically. The logical address has two parts, namely the page number and the offset. The Memory Management Unit of Operating System, abbreviated as MMU, converts the page number to the frame number. You can see here in the diagram, this is the page table, and the page number is converted to the frame number with the help of MMU so that we can retrieve the information from the physical memory. Next, combining these two, we have a concept of segmented paging. Main memory is divided into variably sized segments which are then divided into smaller fixed size pages on disk in segmented paging. Each segment contains a page table and there are multiple page tables per process. Each of the table contains information on every segment, while segment table has information about every segment. Segment tables are mapped to page tables and the page tables are then mapped to individual pages within a segment. Now there should be some advantages also as to why we are using this concept. So some of the advantages include less memory usage, more flexibility on page sizes, simplified memory allocation, and an additional level of data access security over paging. The process does not even cause any external fragmentation also. Now let me give you a brief introduction about Solaris. Solaris is a Unix operating system originally developed by SUN Microsystems. Solaris has a reputation for being well suited to symmetric multiprocessing supporting a large number of CPUs, and it is programmed in C. Talking about Solaris memory architecture, Solaris breaks virtual memory into segments and then these segments into pages. Physical memory is divided into fixed size pieces called pages. The size of the pages vary from platform to platform, but the common size found in Solaris is 8 kilobytes. Each page is associated with a file and an offset. The file and offset identify the backing store for that page. Hardware MMU maps these pages into physical pages by using the platform-specific set of translation tables. Now, in this diagram, you can see that the virtual memory is divided into varied size segments called as virtual memory segments, which are in turn further divided into small pieces called as pages. The physical memory is also divided into pages, and the mapping from the virtual memory to the physical memory is done with the help of MMU. Now, let's just understand the backing store a little bit and some of the terminologies which we'll be using further. Backing store is the location to which the physical page contents will be migrated when that page needs to be taken for another process. The pages are migrated to slower medium like disk, and that is called swap space. The location where the pages are migrated is called page out. When again that pages are needed by the process, the location from which the pages are read back again is called page in. Now in Solaris, two basic types of memory management manages the allocation as well as the migration of physical pages of memory to and from the swap space. The first one being swapping and the second one being demand paging. Swapping is a memory management scheme in which any process can be temporarily swapped from main memory to secondary memory so that the main memory can be made available for other processes. The thing to remember is that swapping is used only when data is not present in RAM. If the memory is consistently less, the memory scheduler starts looking for processes that can be completely swapped out. Now, based on the amount of shortage, we can divide it further into soft swapping and hard swapping. In soft swapping, if the process have been inactive for at least max SLP, that is default set to 20 seconds, then memory scheduler swaps out all the pages for that process. Whereas in hard swapping, the following three conditions should be satisfied. First one being, at least there should be two processes on the run queue waiting for the CPU. The average free memory over 30 seconds should be consistently less than the minimum, and there should be excessive paging. Now, talking about demand paging, the demand paging model uses a page as the granularity for memory management. Pages of memory are allocated on demand. When memory is first referenced, a page fault occurs and memory is allocated one page at a time. According to the concept of virtual memory, in order to execute some process, only a part of the process needs to be in the main memory, which means that only a few pages will only be present in the main memory at any time. However, deciding which pages are needed to be kept in secondary memory is going to be difficult because we do not know in advance which pages should be in the secondary memory and which should be in the main memory. Demand paging is implemented with the help of a page scanner. The page scanner is a kernel thread which is awakened when the amount of memory on the free page list falls below a system threshold, typically 1/64 of the total physical memory. Scanner tracks pages by reading the state of the hardware bits in MMU. MMU bits maintain the state of referenced and written bits, and it uses a two-handed clock algorithm to determine the eviction. Now let's take a look at this algorithm and how it works. In this diagram, you can see both hands rotate clockwise. The front hand clears the referenced bits and modified bits of each pages, whereas the trailing back hand then inspects the referenced and modified bits sometime later. So in this way, the demand paging is implemented. Now before finishing, let me just give you the pros and cons of swapping as well as paging. Talking about the pros, this is the inexpensive way to conserve memory and it is easily implementable. Whereas the disadvantages include, it dramatically affects a processor's performance. Now talking about the advantages of paging. In paging, loading pages of memory on demand dramatically lowers the memory footprint and startup time of the process. So that was all from my side. You can find the PDF in the description below and feel free to put your doubts in the comment section. Thank you so much and goodbye.